Hello everyone. In this video we are going to discuss the magnetic poles, how they exert force on each other. We are also going to explain the SI unit of magnetic poles. We are going to discuss that SI unit, as well as we are going to discuss magnetic dipole moment, both for a bar magnet as well as for a current carrying loop. So go through the video very carefully and see to that everything is clear. At the end of the video, if you have any doubt, then you can post me the doubts. So here we start with magnetic pole strength and magnetic dipole moment. But to understand this very clearly, we need to first understand the force experienced by one magnetic pole due to some other magnetic pole of another magnet. So let us see how we can find the value of this force. The same Coulombs law will be used to find the value of that force as we have used for charged particles. If you are given two charged particles, then the Coulombs law is used to derive a relation for the force experienced by the two charged particles. The same law will be considered for two magnetic poles. Like suppose we have two magnets here, if you can see here, having magnetic poles having strength M1 and M2 respectively. You can see for a particular magnet, the pole strength is same for both the south pole as well as the north pole. For another magnet, the pole strength is different, but it is same for the same magnet, that is for the north and for the south pole. Now, one magnetic pole has a pole strength M1 and another has a pole strength M2. And suppose we are considering the two magnets having their north pole facing each other. So we all know, like, if they are like poles, then there will be repulsion. So the poles, the north poles, each one of them exert F force on the other and they repel each other. And according to Coulombs law, this force is directly proportional to the product of the pole strengths and inversely proportional to the square of the distance between them, as we have considered for charges. Okay. Now, the force is proportional to this value. So if we put an equal sign, then a constant of proportionality will come, and this constant of proportionality, which is given by K and can be calculated experimentally, and the value comes out to be mu naught by 4 pi, where mu naught is the absolute permeability of free space, which you have already studied in the previous videos. Now, the unit of mu naught by 4 pi, the value is 10 raised to the power minus 7 Tesla meter per ampere. But Tesla can be written as Weber per meter square. So that's why Weber per meter square, if we write it instead of Tesla, then the unit becomes Weber per ampere per meter. Now you need to understand here, Weber is the unit of magnetic flux. Phi, if we represent magnetic flux by phi, which is given by B dot A. So magnetic flux, the unit is Weber, which is equal to Tesla meter square. So Tesla is given by Weber per meter square, which we have put here. The magnetic flux we will study in the later videos. Now, the formula for the force will be now given by, instead of K, we will be writing here mu naught by 4 pi M1 M2 upon R square, where mu naught by 4 pi, the value is 10 raised to the power minus 7, so we can write it in this form. Okay. Now see, if we want to find the unit of pole strength, the unit of pole strength is ampere meter, the SI unit. Now suppose we consider M1 and M2, that is the pole strength of the two magnetic poles of separate magnets, be given by M. Both are equal. Say M1 and M2 both given by M. The distance between the two poles be 1 meter, and the force between them, if it is 10 raised to the power minus 7 Newton. So if we put these values in the equation, above equation, so it is 10 raised to the power minus 7 is equal to, this is the value of force we are putting, is equal to 10 raised to the power minus 7, this is the value of 4 mu naught by 4 pi into m, that is m square by 1 square. We are putting the values which we have considered here. So we finally get m square is equal to 1, that is m is equal to 1. So m, that is the pole strength, is 1 ampere meter. So now we can define 1 ampere meter. See here, 1 ampere meter, the pole strength of a magnetic pole is said to be 1 ampere meter. Condition is if it repels an equal and similar pole. Okay, since we are writing here repels, so it will be an equal and similar pole, because both the pole strength we have considered as m, with a force of 10 raised to the power minus 7 Newton when placed in vacuum or air at a distance of 1 meter between them. So I hope this is very clear to you. This is the definition of 1 ampere meter, which is the pole strength. Okay. Now let us discuss here one more important point, that is the magnetic dipole moment of a bar magnet. If you remember, in electrostatics we have studied electric dipole moment. The direction of electric dipole moment was from the negative charge, that is minus q charge, to the plus q charge, and it was given by P is equal to Q into twice A. Now here we are going to discuss magnetic dipole moment of a bar magnet. You need to understand, like within quote you can think this bar magnet, like magnetic dipole moment, we are going to describe two different ways to find the magnetic dipole moment. One is for the bar magnet, another is for the current carrying loop. So first of all we are going to discuss it for the bar magnet. See, we have taken a diagram for this bar magnet. You can see here it has a south pole and a north pole, and which are separated by a distance of twice L. Don't get confused, the arrow should be from the south pole to the north pole, and the total distance here from the south pole to the north pole, that is the magnetic length, is 2L. Okay. Now the pole strength is given by small m. Always remember, the magnetic dipole moment of a bar magnet is actually the measure of the force which it will exert on another magnetic dipoles brought near it. Okay. So when we consider this magnetic dipole moment, it is always directed from the south pole to the north pole. So magnetic dipole moment is represented by capital M with a vector sign which shows that it is a vector quantity, and the direction is always from the south pole to the north pole. Now see here, I am just reading out the definition. The product of the strength of either of the pole and the magnetic length of the magnet is the magnetic dipole moment. So product of either of the pole strength, that is M, into twice L is the distance from the south to the north pole, that is the magnetic length. So M into twice L will give the value of magnetic dipole moment. If you remember the electric dipole moment, so it is analogous to that of the electric dipole moment, where we have written for electric dipole moment it is P is equal to Q into twice A. Now here an analogous situation is there where we are going to write the magnetic dipole moment as M into twice L, where capital M represents the magnetic dipole moment and the small m represents the pole strength. Now magnetic dipole moment is always a vector quantity and its direction is from the south pole to the north pole. That you need to understand. Now if you see here, the magnetic pole strength has a unit of ampere meter and the length has a unit of meters, so it will be ampere meter square. SI unit of magnetic dipole moment is ampere meter square. So I hope this is clear to you. Just now we have explained that how magnetic dipole moment can be represented for a bar magnet, but we know that current carrying conductors also behave as a magnet. You have seen it that when a circular current carrying conductor is taken in the anti-clockwise direction, the phase where the direction of current is anti-clockwise, it behaves as the north pole, and the clockwise it behaves as the south pole. So that means a current carrying loop also behaves as a magnet. So naturally it must have a magnetic dipole moment. So the magnetic dipole moment cannot be calculated by the same formula as we have done for the bar magnet. There is some different formula that we need to follow. So let us see that condition. See here, what we are going to do is we are going to find the magnetic dipole moment of a current loop. The loop of the current can be of any shape. It can be circular, it can be rectangular, it can be any irregular shape, but it has to be a proper loop. So the magnetic dipole moment of a current loop, that we are going to discuss here. Now to understand the concept here, we are using a diagram. You can just see here. This is the wire which is shown here, which carries a current. This is not the current, sorry. The circular wire you can see here, it carries a current I. Okay. Now this circular wire which carries a current I, it behaves as a magnet, because if we see it from the above portion, like from the top view, the direction of current is anti-clockwise, so this phase will behave as the north pole, and the phase which is below will behave as the south pole. So it can be considered as an equivalent magnet, bar magnet, having a north pole at the top and south pole at the bottom. So this behaves as a magnet. A current carrying loop behaves as a magnet, so it will have a magnetic pole. The direction of the magnetic dipole moment here also will be from the south to the north, because north is at the top, the phase which is in the upward direction. So from north the magnetic lines will be coming out. So this will be the direction of magnetic dipole moment. And further, this value of magnetic dipole moment can be explained in the way as mentioned here. Just see here, the magnetic dipole moment of a current carrying loop is directly proportional to the value of current. That is, more is the current, more will be the dipole moment, and it is also directly proportional to the area of the loop. That is, more is the area of the loop, more will be the magnetic dipole moment. So the magnetic dipole moment is proportional to I into A, current into the area, or which is equal to K, which is a constant quantity, I into A. Now this value of K, proportionality constant, comes out to be 1 when we consider current in ampere and area in meter square. So the value of magnetic dipole moment will be written as M is equal to I into A, current into area. Now magnetic dipole moment, we all know it is a vector quantity, so area is also a vector quantity, so M is equal to I into A. And you can see the area vector is always perpendicular to the surface, and which actually gives the direction of magnetic dipole moment. So vector M is equal to I into vector A. The term here, suppose there is n number of turns. So in that case, if there is n number of turns in the coil, so it will be NIA. The dipole moment will be given by NIA, where NI is known as ampere turns. That means the magnetic dipole moment of a current loop, if it is having n number of turns, then we can write here ampere turns, that is Ni, into the area of the coil. So I hope this is very clear to you. We have the dipole moment, magnetic dipole moment, represented in two different ways. For a bar magnet it is M into twice L, and for a magnetic dipole which is in the form of a current carrying loop is given by I into A. So go through the video very properly and see if there is any doubt, then post me.